I'm going to sketch the graph of a logarithm function before we get into this logarithm inequality. And I'm just going to call this the W axis. And the logarithm, and y'all, I should say, I'll call it log base b. And we're going to assume that b is greater than 1. So log base b of w, okay? Now remember, the logarithm returns an exponent. It's the exponent you would apply to b to get w. Now the logarithm, any logarithm function that has a base greater than 1 is going to pass through this point 1, 0. And that's because anything raised to the 0 power is 1. And remember, a logarithm does return, it goes to this point basically because b to the 0 is equal to 1. Okay. Now, the graph of the log function looks like this. Again, we're assuming the base is greater than, it would be symmetrical about the vertical axis if it were less than 1. Okay, so it looks like that, and what we can see right here is that log base BW is less than 0. Let me just write it. Log base B of the input argument W, I left the B out, but log base B of W is less than 0 if 0 less than W less than 1. Okay. And you can see the graph here. This is just the inverse function of an exponential function, and it looks like this for the very same reason an exponential function looks how it is above the W axis. But anyway, from right here to here, the graph of this function takes on negative values. And so log base B of W is strictly less than 0 for W values of W between 0 and 1. Notice that log base B of 0 is undefined. Okay, it's the same. It's for the same reason that let me write this just UNDF, undefined. It's undefined for the very same reason that the x-axis is always above, the exponential function is always above the w-axis. It's the very, very same reason. So you see log base b of 0 is an undefined condition. Okay, so what we're trying to do right now is find all intervals of real numbers such that log base, we can call this log base 10 if you want to. It's only important that it's a base greater than 1. That this input argument is going to kind of stretch things out a little bit. You see, this was just based on w as your input argument. Here we have x squared minus 4x plus 17. We want to find all intervals of real numbers, and an interval is just a compound inequality, basically. Now, so this, we're looking for this to occur. So that means for this very same reason that w was squeezed between 0 and 1, we have to squeeze x squared minus 14x plus 17 between 0 and 1. And we really only have to think about less than 1 than exclude, just set this equal to 0 to find out the rest of the information. So let's see how that goes. Okay, now we do a complete the square here, folks. This is standard here. 7 squared is 49. We have to subtract that off. But when you expand this out, you still get the minus 14x. But you end up with, this would be less than 33 when you do the arithmetic here, okay? Now notice that I wrote something here that takes, I think some people still don't know this, some people are uncomfortable with it, but remember that the absolute value function, the absolute value of b, let's call it b, is the very same thing as the square root of b squared. It's kind of like the norm, Euclidean norm is defined, all right, except it's just for one variable. Okay, so the absolute value of a number b, a real number b, is the square root of b squared. And so you see, that's exactly what I've done right here. I've replaced x minus 7 quantity squared, which resulted from the complete the square process, with absolute value right here, and then square root of both sides. Okay. So you see, that's exactly what happened here. We appeal to this known truth to rewrite this as an absolute value expression, but it's known that when you have an absolute value, you can rip away the absolute value bars by just doing this, okay? It's going to be trapped between minus root 33 and plus root 33, x minus 7. And that produces this interval, okay? Now, y'all, again, this interval numbers just means all the x's trapped between 7 minus root 33 and 7 plus root 33. Now, we're effectively already done right now, but we do have to be cautious about when x squared minus 14x plus 17 equals 0 can equal to 0. Remember, because it is undefined. The logarithm is undefined at 0. And so we have to exclude any values of x such that the input argument is equal to 0. That makes sense. That's just logical. So again, we complete the square and we get these are the two values that have to be excluded. And so the way you would write this out, it'll take a little bit of time to write this down, but I need to incorporate this into this interval as endpoints, so to speak. Okay, so I'll just see if I have room here. We'll have 7 minus root 33. Okay, we're starting at the very same spot that we did right here, but we're having to incorporate these two values of x that need to be excluded. All right, and so you would have 7 right here. Let's see, let me put a comma here. So that'd be 7. I should just write minus root 32 so it's clear. You know, there's no need to simplify it like I did right here, really. Okay, so you see this. It's very clear that this negative number is to the left of this negative number, right? So that's 1. Okay, now we're going to union. Remember, these are just sets of numbers, folks, sets of real values. And so now we have to, the parentheses mean you exclude. Okay, and so we start with 7 minus root 32 again. Okay, and this time we're going to run into this endpoint right here. Okay, 7 plus root 33. Okay, or let's see, we have that, and then we have to do this again, and then we have 7 plus 4 root 2. And I'll just write that as 7 plus root 32. Again, it's just a little easier to see it. Okay, and again, union with 7 plus. It's kind of crazy. We're just trying to exclude values, and this notation is a little cumbersome. But we have 7 plus root 32, and then 7 plus root 33. And I think I got that written down correctly. Okay, so this is this union of intervals, sets of real numbers. Again, 7 minus root 33 was the smallest value, and it got punctured by 7 minus root 32 and 7 plus root 32. And notice it did end at 7 plus root 33. So this is your solution set right here. And again, a lot of people don't like this. The set builder notation is a little more explicit, but this U stands for the set theoretic union of two sets, okay? And the parentheses here, had we wanted to include 7 minus root 32, we would put square brackets right here. But the parentheses means to exclude the endpoints and include everything between the two values, the left endpoint and the right endpoint. So I think I got it right there. I don't think I typoed anything right here. Let's see here. Yeah, up to 7 plus root 32. It starts again, then 7 plus root 33. So yeah, you could actually substitute this into a graphing. Substitute this expression in Wolfram or Desmos or somewhere, your favorite place that graph stuff, and you'll see that this corresponds. This graph would be negative exactly on these interval of numbers here, and you can get an idea about how long it is, right? It's just 14 long. It's basically it's a length of 14 with some points omitted, right? You go from 7 minus root 33 to 7, and so when you the difference, or no, is it more than that? No, it's 7 plus 2 root 33 long. Excuse me, it's 7 plus 2 root 33 long. But that for that interval, you would see this graph below the x-axis. All right. That's it. Good night.